Hey everyone, welcome back, and we're now moving on to question 16 in the 2019 B test. This problem actually is one of my favorite rotation problems because it actually covers the entire, almost everything you need to know about rotation in the F equals ma level. The question reads, a hoop of radius r is launched to the right at initial speed v0 at ground level. As it is launched, it is also spun counterclockwise at angular velocity 3v0 over r. So here's the situation. Initially, you have this hoop that is rotating in this direction, and it has this velocity v0 going forward, and rotation initial is 3v0 over r. The coefficient of kinetic friction between the ground and the hoop is uk. How long does it take for the hoop to return to its starting position? So before we start on this problem, let's kind of think about what is going on in this scenario. The velocity is moving to the right, but as you can see, the angular velocity is rotating in the opposite direction. As you can tell, like if you can imagine, like you just spinning a hoop counterclockwise, the hoop is going to try to roll back to you, right? So that's what's going on. But we want to know exactly how long it takes, and for that we can set up these two equations that will always work for rotation, which is net force and net torque. Okay, so what's going on in this picture is that there's a force of friction pulling it backwards. Remember, force of friction, this is going to be very important for this problem, that the force of friction always opposes the motion. Okay, so the force of friction is going here, or the force of friction always opposes the direction of movement, right? So the force of friction is pointing to the left, so I could, if I say that going to the right is positive, going to the left is negative, then that means that for the net force is negative F, and that's equal to ma. And we think about the torque is also going to be force times the radius of the circle, right? Whether or not it's positive or negative, it doesn't. Well, we'll call it negative, and the reason is because the force is opposing the direction of the torque, initial torque, right? Or the initial rotational motion, because this is going clockwise and this is going counterclockwise, and that's equal to I alpha. Okay. So the general strategy here, after we got these two equations, we can figure out how long it takes by using kinematics 1/2 a t squared. We can figure out how long it takes for it to stop, for all this v0 to go to 0. And then we can figure out the time it takes for the hoop to regain its speed backwards and get to the initial position again. So this is going to be quite lengthy, but let's start. So we can see that the acceleration is negative f over m. So that means if we set up the kinematic equations, so the distance it travels, delta x, is equal to negative 1/2 f over m t squared plus v0 t, right? But we also can say that when it reaches zero velocity, 0 is equal to negative f over m t plus v0 t. So, oh sorry, plus v0. Okay, and so actually using this, we can figure out t real quick. T is equal to v0 times m over f, right? From this equation right here. So then we can plug in t up here to get the delta x, that distance that it travels before it stops moving. But we don't need to worry about this yet. The reason we want to calculate delta x, you might be wondering, well, the question is just asking for time. Why do we need to calculate delta x? We also need to know how much distance it travels, and then we can use kinematics again to see how long it takes for it to travel that distance back to the original position. So this is the time it takes for it to get to the position where v0 equals 0, right? Now let's consider the net torque. Okay, so what is the angular velocity when the translational velocity 0 when this time is reached? Well, we know that the angular acceleration alpha is equal to negative fr over I. And what is I? It says it's a hoop, right? A hoop. So the moment of inertia of a hoop, if you have memorized it, it's going to be just mr squared. And if you don't memorize it, the reason this is the case is because all the mass elements of a hoop are equally spaced from the center of the loop. So that means that they're all, you can consider them all to be the same point, basically, away from the center of the center of mass. So that's why it's mr squared. So we can simplify this down to negative f over mr, right? Okay, now let's talk about, hold on, let me get rid of this thing real quick. This is the next problem. So we set up the kinematic equations for rotational velocity, then we have, well, we actually don't need to do delta theta because that doesn't mean anything to us. But we can figure out exactly what is the angular velocity final when velocity final is equal to 0, right? Because this is when velocity final is equal to 0. And that's negative angular acceleration times time plus initial angular velocity, right? And we know what the time is. We calculated the time it takes for the velocity to reach 0 here. So then we just plug that in, negative, I'm going to plug it in also to here. Plug in the angular acceleration. We already accounted for the negative sign, so I'm just going to keep the negative here. Negative f over mr times t, which is m v naught over f. And then plus the angular velocity. Actually, I'm going to plug in the angular velocity in terms of v naught, so that's 3 v naught over r. So if we simplify this down a little bit, I'm just going to use capital R for everything, even though they give us in terms of lowercase r. So these guys cancel out, so we actually get this is equal to negative v naught over r plus 3 v naught over r. So that means that when v final is equal to 0, the angular velocity has still v 2 v naught over r. So let's think about this situation real quick. What this situation is talking about is that the velocity is not moving at this instant of time, but the angular velocity is still moving at 2 v naught over r, right? So if we can just imagine that we spun a hoop and then we just let it on the ground, what's going to happen now is that the velocity is going to start moving in this direction, right? And remember, friction always opposes the motion. So as you can imagine, as the hoop is sliding on the ground, the friction is going to continuously scrape against it and move it in this direction, but also slow down the angular velocity, right? So here the friction is pointing in this direction, right? Because it's trying to oppose this angular velocity that's scraping against the ground. And that makes sense because this friction is also causing this velocity of the center of mass to go forward, right? So if we again write down the net force and net torque for this situation, net force is still the same, the force of friction times ma, except that now I'm going to call it the positive friction because it's adding velocity instead of subtracting velocity. And net torque is going to be still negative because it's subtracting from 2v naught over r. Negative f times r is equal to I alpha. But before we move on, I just wanted to make something clear real quick. The question is, will this continue to reach 0? So basically, will the angular velocity keep decreasing from this negative torque? Will it keep decreasing and decreasing until it becomes 0? And the answer is no. And the reason is because once it reaches a point where it starts rolling without slipping, or where velocity center of mass is equal to the angular velocity times r, once it reaches this point, recall that it does not undergo kinetic friction anymore. It undergoes static friction. and because of this, it actually doesn't lose any more speed. It actually reaches a point where it starts rolling at a constant velocity. So we have to be careful when we're using these equations. Once it reaches the point where v center mass equals omega r, which actually we can make it a bit more concrete, which is going to be, let's see. So, well, here, let's just write down the kinematic equations first. So so we have delta x again for the force is equal to, this time is positive acceleration, so F over m, 1/2 F over m t squared plus, well, there is no v naught in this instance because it's starting from rest. And we know that the angular velocity final is equal to negative fr, okay, negative fr over I, we already calculated up here to be just negative f over mr. So negative f over mr. Okay, and then times time plus, I'm going to call this time 2 for the time that it takes for it to get back to the original position, plus the, and this is final 2, but this is the omega final right when this instance starts, which we calculated right over here. So now we can try to find this time. The goal again is to find this time t2 that it takes for it to reach back to its original position. And then we'll add up t1 and t2. I'll call this t1, the time that it takes for it to get to the point where it starts moving backwards, and then it's plus the time it takes for it to get back. So how do we simplify this? We know what delta x is. We can calculate it from this equation up here, right? So actually, let's not do that yet. But also we have to be careful because we have to make sure that the angular velocity of the final, once it reaches the once we multiply this by r and it reaches the velocity of the center of mass, it doesn't lose any more angular velocity, right? So what we can do is, well, let's first calculate delta x that it takes, that it's trying to reach. So this is equal to negative f, negative 1/2. Here, let's see. This is equal to, if we plug this in, this is negative 1/2 f over m t squared. So this is t, m squared v naught squared over f squared plus v naught t. V naught, and this is v naught over f. So we can cancel out this guy. We can cancel out this guy. So this is negative 1/2 m v naught squared over f plus m v naught squared over f. So this actually is equal to 1/2 m v naught squared over f. So we can simplify this guy down a little bit as well. Oops. So that means that t2 squared is equal to, let's see, that's going to be m squared v naught squared over f squared, right? So actually this comes out pretty well. T is equal to just m v naught over f. And now if we plug this into here, because the answer choice doesn't want it in terms of friction. Well, actually, it could be in terms of friction. Let's see, what did we calculate for up here? All right, so first of all, we could just, so this is the time it takes for it to get back to the original position. So in theory, we could just add t1 and t2 and not give us an answer. But we have to be very careful because this is the time it takes for it to get back from the assumption that the velocity of the center of mass this condition has not been reached yet, because once this condition is reached, the velocity of center mass doesn't change, and the velocity of the angular velocity also doesn't change, right? So we have to make sure that this condition has not been reached yet if we want to just add them together. So let's first see what the actual angular velocity final is by the time that it reaches the original position again. So this is negative f over mr, and then plugging this into T2, m v naught over f plus omega final, which we calculated above to be 2 v naught over r. Okay, so this cancel out. So again, it loses another v naught over r, so then it gets 2 v naught over r minus v naught over r is equal to v naught over r. So this is the final angular velocity. And actually, if we plug this into this equation, see if it follows this scenario now. If we multiply by r, okay, so hold on, so v center mass, omega times r, so what's this times r is just v naught, right? V naught over r times r is equal to v naught, and this is equal to velocity of center mass. Or is this equal to velocity of center mass? Is the question that we're trying to look at right now. And what is this velocity of center mass? Well, if we just use the kinematic equation, the velocity of center mass is equal to the acceleration times time, right? Plus v naught, and v naught is equal to 0 in this instance. So acceleration, as we already calculated, is f over m. So f over m times this time that we calculated, m v naught over f. Cancel these guys out. Okay, so we get v naught, and that's really interesting because the velocity of center mass is also equal to v naught. So what we actually calculated here is that at the exact instant where the hoop goes back to the original position is when it starts to roll without slipping. Where it starts to follow this equation. So what we calculated here is correct, right? Because during this entire time, it's following this equation. Now, what happens afterwards, after it reaches the original position, is actually that it continues rolling at this constant speed, velocity of center mass, which is equal to v naught, right? It doesn't get any faster, it doesn't get any slower. But for our purposes of this question, the velocity, the time is given in these two equations. So if we just add them together, they're actually the exact same. So we should get 2 mv naught over f, and f is just the mu times the normal force, which is mg, right? So we can plug that in, so that's 2 mv naught over mu mg, so we cancel out these guys, so that's 2 v naught over mu g. That gives us 2 v naught over mu g right here. Answer is B.